Another method of acquiring charge is known as charging by conduction. This is probably the one you're most familiar with. Most of the times you've gotten a static shock in your life, it has most likely been as a result of touching something, and that is generally charging by conduction. So before we really understand what charging by conduction entails, we do have to understand two different um, types of materials in terms of electrical properties. And I'll use this as a quick example. Let's say, I don't know, someone decided to take a metal fork and to stick it into an outlet. I mean, aside from the fact that we have circuit breakers and things that should protect us, that's not going to be a good situation because we could potentially electrocute ourselves. So it's not a wise decision. However, if we tried to do the same thing with a plastic fork, we'd find that nothing really happened. And we could walk away and we could pretty much be safe from that situation. And what we have to realize, I think most people understand there's a difference between the fact that the fork is made of metal and plastic in those two situations. And we have to understand that one of these materials is a conductor. So a conductor is a material that allows the free movement of electrons. So as an example, if we had like a conductive sphere, this kind of bronze colored, if we had a conductive sphere and we took a wire, electrical wire, and we made contact, those electrons could actually spread out and flow onto that material. They could continue to flow onto the material. New electrons from the wire would come in, and they had free range to move anywhere around the sphere that they would like. You could even place another wire on the other side, and the electrons could actually travel from one wire through that conductive material and then into the other wire. And if you took like a lamp cord, like a light, and you cut the cord and you stuck both ends on the opposite side of a conducting sphere, like that lamp should still be able to light because the electrons can travel through that material. Examples would be like metal, so gold, silver, copper, iron, natural water with salts. When I say natural water, I mean like water you'd find in a lake, water you'd find outside that's kind of either seeped through the ground or through evaporation has some kind of dissolved salts in it. Pure water is actually not a very good conductor, but that's why they say like be careful in pools, right? It's chlorinated. There's lots of salts and minerals in there. Human beings are conductors. That's why we have to be extra careful with that metal fork situation because our own bodies can conduct electricity. The other material, the plastic fork, that would be what is known as an insulator. An insulator is the opposite. It does not allow for the free flow of electrons. Yes, you can place an electron on an insulator, but they're not going to have free movement. So if we use the same electrical wire example, while if I move that wire around, electrons may be able to jump onto the surface of the insulator, they are then stuck in place. They cannot move around and freely flow. If I move that wire around to different parts of the insulator, I could probably get some electrons to jump onto those spots. But if I were to connect a wire like I did before, you wouldn't find that any electricity would flow because the electrons, outside of being placed on a specific point on the surface of an insulator, they have no ability to actually flow. They can't really jump from atom to atom based on the molecular makeup of that material. Examples would be anything that doesn't conduct electricity. So cotton, silk, rubber, paper, glass, cork, wood, which I already said. Anything that doesn't conduct electricity is going to be considered an insulator. In the real world, there are certainly materials that have properties like in between. You may have heard terms such as like semiconductors and things like that. We are mainly going to be concerned with full conductors and full insulators, materials that allow the free flow of electrons and materials that prevent the free flow of electrons. It's actually why there's insulation on a wire when you think about it. The insulating wire is usually made of plastic or rubber that allows you to handle the wire without getting shocked. But inside is a copper core usually, or some kind of metal, and those electrons can free flowly through the center of that wire without actually coming in contact with our own conductive hands. So the latex or the rubber coating on a wire protects our conductive hands from the conductive metal inside, does not allow electrons to flow through that insulator. All right, now that we understand those two terms, actually charging by conduction occurs whenever you have two differently charged conductors that make direct contact. So what I mean by this is we would have maybe a positively charged metal sphere and a negatively charged metal sphere. Therefore, I have different charges, and if I allow them to just physically make contact, if I'm an electron, I want to get away from other electrons, and I enjoy positive spaces. So the electrons in this case would flow from the negative to the positive object because electrons are attracted to the positive charge on the leftward object and repelled by the other negative charges on the rightward object. So that's why that net flow of electrons will always be towards the more positive object, because that's what electrons prefer. A simple analogy that I like to use when trying to visualize what's going on with conduction, I refer to as kind of like the cup analogy. So if you imagine you had 2 cups of water that had the same exact amount of water, we'll assume same size cups and everything. If you jammed a straw in the bottom and they both began with the same level, nothing would happen. You'd have no flow because there's no difference in the amount of water that each has. Just like if you had 2 equally charged objects and you allow them to touch, you wouldn't have conduction because an electron doesn't prefer to be in one of those objects over the other. They have the same charge. So conduction occurs when you have 2 different amounts of charge, just like if you had 2 different levels of water initially in these cups and then you jammed a straw in it. In this case, there would be a net flow. You'd have water from the fuller glass flowing through that straw into the water, the cup with less water, until that point where they both have the same level. Once they have the same level, there will be no further transfer of water between those cups. And it's very, very similar with electric charges. If I had 2 charges, 2 charged objects, a -4 coulomb and a +2 coulomb, if I allowed them to make contact and they were conductors, electrons would jump from the negative object to the positive object. That would continue to happen until both had the same charge, which in this case would end up being -1 coulombs. Just to explain quickly how I got to that value, the -4 is going to transfer at least 1 negative coulomb to the other. And when that happens, the -4 will now have -3 because it gave some electrons away. It gave away -1 coulomb. And the -1 coulomb decreases the +2 coulombs by +1. So I'm just taking 1 negative coulomb and transferring it from the left to the right object. However, there's still a difference, so conduction will still occur. So once again, we'll take another -1 coulomb and transfer it from the left object to the right. So by taking away 1 negative coulomb from the leftward object, it ends with a -2 coulomb charge. And by gaining a -1 coulomb charge, what was originally +1 coulomb is now neutral, or 0 coulombs. There's still a difference, so that happens again. We transfer another one, and at this point, they both have -1 coulomb, and there's going to be any further transfer. I'll go into that in more detail, so don't be too concerned if you didn't fully follow that, but it's just like the 2 cups. Electrons will keep going and transferring from the more negative to the more positive object until you reach the point at which they both have the same charge. Again, this is assuming the same sizes of the conductors and whatnot. All right, so to give you the conditions that you must meet in order to charge by conduction, just like we did with charging by friction, there's 3 of them. You must start with differently charged conductors. A lot of people want to say opposite, but you don't necessarily need to have a positive and a negative. You could have a positive and a more positive object, or a negatively charged and a more negatively charged object. As long as there's a difference, there will be flow, just like with those 2 cups of water. As long as there is a difference, there will be a flow. You do not have to have 1 full and 1 empty, just a difference will do. You then allow them to make direct contact, and as stated, you end with 2 equally charged objects. Now, they're not exactly the same size, like one very large sphere and one very small. It's a little bit different. It might not be exactly equal, but we are only going to be looking at equally sized, geometrically equivalent objects for the purposes of this course, so it's safe to assume when those conditions exist, you end with equally charged objects because there's no longer any reason for electrons to want to flow from one of the objects to the other. In the following videos, I'll show you a few examples going over the kind of the basic math that I showed you quickly in the last slide, and show you how we can use conduction and some mathematical principles to determine exactly how much charge is transferred, what the total charges will be, etc.